Our speaker today is Andrew Gettelman, who's a senior scientist here at NCAR in ACOM and CGD. Andrew specializes in developing global models with specifically cloud aerosol interactions. He works on physics and chemistry in the upper troposphere and lower stratosphere. He's a member of the atmosphere model working group here, as well as the co-chair of the whole atmosphere, or ACOM, working group. He's a contributing author and reviewer to international scientific assessments on climate change and ozone depletion. He got his PhD from the University of Wisconsin and his bachelor's from, Washington.
I copied somebody else's bio. I want to make sure I changed it right.
I had one job. His bachelor's from Princeton University.
Okay. Thanks, Mike. So this is going to bring together a number of threads, and I think it's been this is kind of an interesting project. I'm going to talk about the troposphere, I'm going to talk about the stratosphere, I'm going to talk about observations, I'm going to talk about global models. So it's going to bring together a bunch of different things for a bunch of different parts of the field. And of course, in doing that, this is going to have a lot of co-authors. Many of them are actually in the room, including most of the ACOM team and Anya Schmidt from the University of Leeds. This is also, Mike has done a lot of the work on the stratospheric volcanoes that I'm going to show, and Jennifer Griswold at the University of Hawaii and Jeff Stith, also at NCAR, have done a lot of work, and we're working with now on some of these observations. So what I want to talk about is the impact of volcanoes on climate and air quality. And there's a couple different things going on when we think about volcanoes, of course. There's two kinds of volcanoes. There's eruptive volcanoes and effusive volcanoes. Eruptive volcanoes go boom. Effusive volcanoes go boom a lot less forcefully, a lot quieter. What that basically means is we're used to these. You get big ash clouds. They contain a lot of chemical constituents, and primarily what I'm going to talk about today has to do with sulfur dioxide, which oxidizes into sulfate aerosol and gets into the stratosphere here and sticks around for a long time. There's a lot of chemistry that's associated with that. There's also some radiative effects. SO2 also comes out of these effusive volcanoes. Comes out of volcanoes that don't go boom. In many cases, they're not even, you almost wouldn't consider them active, but if you go to any volcanic fumarole or hot springs and you smell rotten eggs, you're getting some of that. And so that comes out of the Earth also. And not only does that have a little bit of an impact on the stratosphere here, and there's a radiative effect because these aerosols end up scattering light, so they're generally a cooling effect. But there's something else that happens in the troposphere because sulfate aerosols are actually very good sites for cloud drop nucleation. So they actually alter the properties of tropospheric clouds. And I'm going to talk about both of these impacts. We typically think about the volcanoes that go boom, not so much about the effusive volcanoes, but I'm going to show these are actually quite important. And they also present us a natural laboratory for understanding some pretty fundamental uncertainties in the climate system. And I don't know if I have a slide on this, so I'll mention it now. But the effect of anthropogenic SO2 and sulfur in general is to also create sulfate aerosols and to also alter clouds. And this is actually the largest uncertainty in our current forcing of the climate system. So this process, as some of you know, is giving us fits as we try to put together the latest version of our community Earth system model. And so it's kind of timely to talk about it. So first we'll start with volcanoes that go boom. This is Mount Pinatubo. So that's the biggest, correct me if I'm wrong, the biggest eruptive volcano since it happened, right, in 1991. It's the largest eruption in the last 25 years or so. This produced a huge amount of ash. It also produced a huge amount of sulfur that got up into the stratosphere and spread around the world. You can actually see it from space. These are refractive layers of sulfate aerosols well above the clouds in the stratosphere. This was taken from the space shuttle about a month after the eruption. And some of you maybe, like me, may be old enough to remember that there were actually some pretty spectacular sunsets in the fall of 1991 in particular. This is from Hawaii in August, and you got all kinds of peachy colors that you rarely see in sunsets. So what this means is there was a lot of scattering going on high up in the atmosphere and the stratosphere that actually acts to cool the planet. This is observations in quotes because it's observations going back through the last millennium or so, so there's not a lot of thermometers back in here. But there was also, this is also a model simulation, and what you can see is some of these large spikes. And these large spikes are generally associated with volcanic eruptions, and I'll show a blown up view of that in a little bit. And this volcanic cooling is actually pretty important, so it's kind of hard to pick out, but Mount Pinatubo is right in here somewhere. These are ones that we do know. This is Tambora, Krakatoa, and Santa Maria. These are the model spikes, and there's, particularly for Tambora, there's a big observed spike in the data as well. So this cooling has actually been used to help us understand climate. And for example, what Mount Pinatubo was quite good at is, Mount Pinatubo was actually a very good, this is a nice paper by Brian Soden. It was a very good test of what happens if you suddenly turn down the sun effectively for the troposphere. You scatter a bunch of radiation away. And what happened is the planet actually cooled. This is microwave sounding unit temperature profiles over a couple years. And then what it tells us is if you apply a forcing to the planet, does a model respond the same way the planet does? So this is an ensemble of simulations from the GFDL GCM in red. And this is the observations with an ENSO signal removed in the black dashed line, if you can see that. But you can see that there's a significant cooling in the model ensemble and in the observations, which is about the right magnitude. And this is actually a pretty good test in this case of generally the water vapor feedback is what you're seeing. You're seeing if the atmosphere gets cooled, there's less water vapor in the atmosphere, that amplifies the cooling a little bit. And there's been subsequent tests of this with other models and other methods, but this is a nice way of actually using volcanic forcing to actually test what's going on with the climate system. There's also been a lot of discussion, and this is some nice work Gavin Schmidt has done, and Susan Solomon with co-authors here has done some work on this too. Small volcanoes actually cool the planet. And what this work actually kind of illustrates is if you take the CMIP-5 model ensemble, which through the early part of the 20th century looks like this with, these are hypothesized forcings because these models were run sometime back in here. And then you actually adjust the forcing to account for a little less from Pinatubo and a little more, particularly from volcanic emissions. That actually results in a cooling because there's a lot of small volcanoes in the recent decade, and that actually shifts the model ensemble updated forcings much closer to what the observations actually are, which is what we have called, people called the hiatus, at least until 2 years ago or a year or so ago when it ended. But this is important also for determining recent climate forcing and in actually determining attribution. So these are mostly stratospheric volcanoes. But there are other effects of these effusive volcanoes. And one I'm going to talk about in particular is, and forgive me if I butcher my Icelandic, but it's not that easy. This is the one that you actually could pronounce. It's called, and I'm going to still mangle it, but it's Bardabunga. That good? That's good. That's good, okay. And you could pronounce it, and nobody really heard about it because as opposed to the volcano that shall not be named in 2010, yeah, that one, as many Icelandic volcanoes do, the fissure comes up under a mountain which has a big ice cap on it, and when the hot lava hits the ice cap, it goes boom. This one was headed for the same thing, and then the fissure went to the side and came out here in an open plain and just created a bunch of lava and some smoke, but really no ash and no explosive emissions. So most of this stayed relatively close to the surface, and it emitted a tremendous amount of basaltic lava and a tremendous amount of sulfur dioxide. It was in a fairly remote region of Iceland. It was not near a major city, well, the major city. It lasted for 6 months from August of 2014 to February 2015. And this was, as I'll show in a minute, I think it was 2 to 3 times, in 6 months, I think it was twice the annual emissions of Western Europe. So anthropogenic emissions of the entire EU. So it's a single point source with a lot of sulfur. And if you look at the sulfur dioxide measurements near the eruption, this is the EPA standard. This is before the eruption. This is the eruption. So the air quality got actually fairly toxic in this region for both livestock and for people. Fortunately, there weren't a lot of people affected. So this on the scale of Icelandic volcanoes is actually somewhat small in eruptions. The largest of the last several hundred years was a volcano called Laki that also erupted for 6 to 9 months between the summer of 1783 and the spring of 1784. There was an initial ash cloud, so this was explosive. And then there were 6 months of SO2, lava, and ash in a series of different eruptions. If you look at, this is sort of the Berkeley Earth temperature record, which is a temperature reconstruction. And again, if you look at the, this red line in here, which is sort of a fit and a smooth fit to the curve, each one of these spikes is a volcano. Here's Krakatoa, here's Cosingua, this is in Nicaragua, this is Tambora in 1815, and this is Laki in 1783. So this is a big effect. This is northern hemisphere land temperatures, global land temperatures, 12-month moving average. And this for Iceland in itself was pretty disastrous. It created, I'm not even going to try to pronounce that, what they call the mist hardships. 25% of the population, 80% of the livestock died in a pretty massive famine. That was due to ash. This is an example after another smaller eruption. It was due to sulfur dioxide. It was also due to fluorine poisoning. There was a significant amount of fluoride that came out, or fluorine that came out, that got basically into the food chain, and it basically killed both livestock and people. And this was even bigger than what we've seen recently. This is about, they estimate about 3 times the annual EU emissions. What was interesting is that while a lot of this went into the stratosphere, a lot of it didn't get into the stratosphere. So the summer of 1783 in Europe was actually one of the hottest on record. And it's hard to see here, but before this cooling, there's actually some spikes in here where things got really, really hot in these temperature records. And those are records from Northern Europe. This is a deviation from temperature where you see something like 3 degrees or more difference in Northern Europe in the summer. There was also quite a bit of basically extensive acid fog and haze that caused some heat waves throughout most of Western Europe. And then the following winter was very, very cold in both Europe and North America. You can see writings about this and discussion of the record cold. Actually, there's some nice quotes from Benjamin Franklin on that in the northeastern United States. There were famines, I think, particularly on the European side of the Atlantic, and there's even people that blame the resulting instability over the next couple of years with a couple other events, and they blame that for the French Revolution and exacerbating it on volcanoes. So these volcanoes happen not just in Iceland, they happen in a number of other places, particularly the effusive sort. One good example is the island of Hawaii. So this is a satellite image in the visible from November of 1995. Here's the Hawaiian Islands here. So this is Maui. This is the big island. So here's Mauna Kea, Mauna Loa. And Kilauea is the current position of the hotspot that created the entire Hawaiian island chain, is now right in through here. And what this is, you can see these island wake effects, but all this haze here is actually sulfate emissions. It's sulfate from the SO2 emitted from a point source here from the Kilauea eruption. And the Kilauea eruption has been going since 1983, fairly continuously. This is, there's quite good data. This is from Tamar Elias at the Hawaii Volcano Observatory, which is run by the U.S. Geological Survey at the National Park at the rim of the crater. And there were some periods, particularly in 2008, where there were some fairly large eruptions, and I'll get back to that in a minute. But it's tailed off over time, but it's been pretty constant at somewhere on the order of 2,000 tons of sulfur dioxide per day. If you work that out into megatons per year, if I did my numbers correctly, this single point source is about 10% of the annual anthropogenic emissions from the entire United States. And this is in the middle of the Pacific. What this does is it creates a significant air quality problem in Hawaii, first of all, particularly on the Big Island. This is a clear day on the Kona coast. This is a day that's affected by what they call a volcanic fog, or a VOG, and it starts to look like a polluted area, like a polluted megacity in an otherwise pretty pristine environment. And what you have is, this is air quality forecasts that are generated by Stephen Businger's group at the University of Hawaii, and they run WRF with the high split, they run a detailed 4-kilometer WRF simulation with high split trajectories and a simplified oxidation scheme to take SO2 and turn it into sulfate and figure out where the air quality gets unhealthy. And here it's still good, but you can see this big plume of SO2 on this particular day is wrapping around onto the Kona coast and actually coming right across Oahu, where Honolulu is. So when they actually have bad smog events on Oahu, it's usually not local. It's actually usually from, again, also from the volcano. So this creates a regional air quality hazard in the Hawaiian Islands itself. And of course, I mentioned the other aspect of this is the interaction of volcanoes and clouds, and this is from a very nice paper that Anya wrote a number of years ago. Sulfur emissions also turn into sulfate, and you get smaller cloud drops because you have more cloud condensation nuclei. That actually results in more reflective clouds. This is what we call the indirect effect, aerosol cloud interactions. And you can see this, for example, in tracks of ships that emit sulfur into the marine boundary layer. You can also see it in volcanoes that emit into the marine boundary layer. So here's 2 islands in the South Sandwich Islands off, this is between South America and Antarctica. Here's one island with a very nice wake vortex, which is not erupting. And here's another one which is erupting. And you can see it actually creates quite a perturbation to the cloud field, which is much smaller cloud drops on this MODIS image of cloud drop effective radius. So what's happening is you get scattering and absorption, you get some direct effects, but you get these aerosol cloud interactions where an increase in aerosols gives you an increase in cloud condensation nuclei, you get an increase in cloud drop number, and that actually makes the cloud brighter. A brighter cloud, particularly over a dark ocean, has a cooling effect. So it's a net cooling effect. The other thing that happens is here you end up with big cloud drops. They tend to more readily precipitate. Here you end up with smaller cloud drops. They may not precipitate as rapidly. So there are other complex microphysical effects that might delay precipitation or give you longer lived clouds or give you even thicker clouds. And right now what I'm talking about is stratiform clouds. If you start thinking about cumulus clouds, this gets even more complicated because then the precipitation process is important for the cloud dynamics. And so the whole dynamical evolution of the cloud changes when you get into precipitation. So some of these effects are pretty easy to observe. It's pretty obvious that if you increase aerosols, you increase cloud condensation nuclei. So this is from a nice review by Danny Rosenfeld, and he looks at a number of different field projects. These are remote regions and these are polluted regions. So you see the remote regions up are here, the polluted regions are up there. There's a pretty good correlation between cloud condensation nuclei and aerosol optical thickness. Of course, you will note this is 2 things. This is a log-log plot, and these are huge error bars. So I'm not sure that that really means a whole lot and that you really want to put 3 significant digits on that exponent. But the whole point is that qualitatively this exists. Quantitatively, it's kind of hard to pin down because there's a lot going on. So here's another example going back to Bardabunga in 2014. So this is a MODIS image. It's a difference. It's an anomaly for the month of October 2014 versus 11 other Octobers in the MODIS record over the North Atlantic. So the volcano is here. And what you can see is you can see a 1 micron perturbation, smaller cloud drop effective radius over the whole month over most of the North Atlantic, which is fairly significant in terms of seeing that big a change in the drop effective radius. What is also interesting, if you look at the same thing in terms of liquid water path, there's not really a clear signal. There's some noise, it's much noisier, but there's no real clear signal there. So what we're seeing is we're seeing changes in effective radius. So we have more cloud condensations, we have increase in drop number, but it's not clear exactly what's happening here with the liquid water path. That's one of the things we're trying to understand. Here's a satellite climatology from the Pacific. So this is now OMI column SO2. And note that this is about 2,500 kilometers. So this is the date line, and this is Hawaii. So this is a pretty good stretch of the Pacific here. And while the SO2 tails off pretty rapidly because it oxidizes into sulfate aerosols, and I should note, this is like a 12-year climatology. So the volcano's been erupting the whole time, but you can see in the climatology this streak in optical depth, high optical depth, right across the Pacific, right from the middle. It's pretty obvious in the satellite climatology. You can also see the SO2, and then you can actually see it also in the cloud drop effective radius. It goes out maybe half the distance there. It's hard to pick out. But again, similar to what was seeing for 1 month from the Icelandic volcano, but this is a decade-long climatology. What of course is hard is to pick out the actual relationships between these things on a process-based level. So now going from the 10-year climatology to a particular day, this is the SO2 plot, and of course the problem is you can't measure SO2 from OMI where you have clouds, and you can only measure cloud drops where you have clouds, so you're not measuring both at the same time in the same place. So what we end up is suggestive evidence. This is OMI SO2. Here's the island of Hawaii. This is approximately the same scale. This is the MODIS effective radius. Blue colors are smaller. So right on the edge here you have a cloud, and there you seem to have smaller cloud drops than anywhere else in this picture. But again, this is hard at this scale to actually quantify anything. The question is what's really going on. Again, this is a qualitative picture. It doesn't really give us a lot of quantitative understanding. The first thing that we worry about is this plume actually in the right place? Because these clouds are low, we know their altitude, and in many cases the aerosols could be lofted above the clouds. Worked with Ralph Kahn at Goddard with the MISER team, and they've done some actual analysis of these plumes. So they take, this is a visible image, but MISER has a bunch of different images, and where they get a thick enough signal off the aerosols, they can actually, they have 9 cameras on MISERs, they make stereographic images, and from these points they can actually calculate an altitude. And these are not clouds, they're actually doing it off the aerosol points. They've masked out the clouds in this picture. And you get a distribution of height. So you actually see that the center of this plume, or at least what's seen from the satellite, is somewhere about 1 kilometer or so above the ocean surface. So this is well into the marine boundary layer and about the same altitude where it actually could affect the clouds. Doing some more detailed analysis to try to understand, and we have a number of different days of this to try to figure out, and they're all pretty similar. I mean, you see spread, but there's no evidence that the plumes are really above where the clouds are. So this is some work that I've been doing with Ed Gerspert at Imperial College, and what he was looking at is we've tried to segment this out. Remember I showed you that 2008 period was a much more intensive eruption from Kilauea, and that's been used by a number of co-authors to say, well, let's look at that as different from other years. So this is 2007. This is aerosol index, so it's very similar to aerosol optical depth. And you can look at aerosol index for 2007, 2008, and 2009. This is latitude and longitude, and it's aerosol index, cloud drop number concentration, and liquid water path. Again, from MODIS, and it's composited for a particular year. And again, it's pretty clear that here's an elevated aerosol index. Here's a change in cloud drop number, which does appear to be elevated farther away from Hawaii in this case. But it's not clear exactly if there's anything correlated going on with liquid water path. And this is some way of looking at the cloud drop number concentration here and the aerosol index here, showing that as you get to higher aerosol index, you see an increase in cloud drop number, but it's not necessarily monotonic, particularly in clean regions, which is interesting and makes things more complicated. So the difficulty in satellites with this is actually, again, we're not very often not observing the aerosols and the clouds at the same point in time. So how do we actually get around that? And the more I've looked at this, the more I think we've actually come to the end of what we can do with the satellite data. This gets you things that are a little more quantitative. So this looks a little better than some of the pictures that I showed, for example, from the Rosenfeld study, but it's still going to give you quite a bit of spread in what's going on. And the other problem is this non-monotonic relation, which means there's some interesting complexities of the cloud microphysics going on. So there's been some sampling of this. So going back to this nice picture. So the reason I picked this picture, of course, is because this was actually during the ACE-1 experiment. And this comes from Tony Clark, who's retired from the University of Hawaii. But one of the things they did is they actually had one flight during this project in the Pacific where they actually sampled the volcanic plume. And I can overlay it. So here's the flight track. And you can see it went out of the plume and into the plume. And they kind of went back and forth trying to sample the plume with an aircraft. And what they did is they actually tried to observe aerosol forcing. And so this is one way to look at it. You can basically measure a series of terms, and this is how we kind of think about it as this chain rule kind of gives you a series of processes. The relationship between the radiation and the aerosols is a function of how the condensation nuclei result from the aerosols, then how the cloud drops result from the condensation nuclei. So there's an aerosol nucleation and an activation process. Then you have a change in cloud optical depth that results from changes in cloud drop number, which is a microphysical term which buries a lot in there. And then from that change in optical depth, you get a change in radiation. So by measuring how these terms co-vary, and particularly from a detailed aircraft observations, you can start to get at some of these things. So for example, if you're measuring SO2 and you're measuring CCN directly from the same platform, you can actually see these relationships and start to quantify them. So of course, this has some instruments, but what you really want is you really want to add a bunch of other things going on in here, and that's one of the things we're talking about doing now. So I want to step back a little bit and now talk about how we simulate volcanoes. And this is getting into some of the aspects, again, of how this plays into understanding past and historic forcing. So again, there's two aspects to this. One is stratospheric volcanoes. One is tropospheric volcanoes. And the nice part about what we've been doing in CESM is traditionally these have been done separately, where the tropospheric volcanoes, we emit SO2 into the troposphere. That SO2 goes through a simplified chemistry scheme. It oxidizes to sulfate aerosol. We have an aerosol model. The cloud, we have an activation code that then activates the aerosols and nucleates the cloud drops and gives us a explicit calculation of that. In the stratosphere, we've simply prescribed a surface area density, which is what you need for the radiative transfer. There's no clouds involved. So now what we're doing in CESM2, which is some work that Mike Mills has led over the last couple years, combined with work that Anya and others have done on, and Ryan Neely has done on generating a volcanic emissions data set, is we've actually extended that to be able to emit SO2 into the stratosphere and have that simplified chemistry scheme or a complex chemistry scheme work to oxidize it and then actually calculate the surface area density from the prognostic aerosols. So here's a database of volcanic eruptions. We have both explosive volcanoes, and there's also a set of effusive volcanoes that come into the model as well. And we've added this basically directly into the aerosol model in CESM. And you can see these here. It's the size of these volcanoes. Lots of little ones. This is Mount Pinatubo here. That's a big one. And again, as I noted before, you can see there was kind of a quiet period up until about 2000, and then a series of smaller and relatively moderate-sized volcanoes picked up over time. So this is a nice video that Mike made for that last decade or so. And what you can see is the volcanoes are these triangles going off, and after that, there's an increase in the sulfate. This is actually once it oxidized, the sulfate column burden happening in the model. So after each of these, it takes quite a bit of time for these to actually get out of the model. You can see it cleans up, and then these volcanoes will emit, and for several months, there's actually quite a bit in the stratosphere. And they have slightly different effects at high latitudes. They also get cleaned out a little bit faster at high latitudes than at low latitudes, and it also depends on the altitude. So this is running in WACOM, so this has actually full chemistry, and it turns out doing the full chemistry is actually important for oxidizing these things. If the OH is not interactive, we've actually found that you don't get the right answer for how these things oxidize in the stratosphere. And looking at this a little more quantitatively, this is a paper that Mike led last year. This is a series of observations in the different colors. And what's plotted here then in black is the model, and the model above the tropopause or the model above 100 millibars. And there's a series of different observations. This is for the polar regions, so it's compared to Ny-Ålesund at 78 degrees north, which is a LIDAR. This one in the tropics is compared to Mauna Loa, which is at 20 degrees north. And you can see actually quite good agreement in the aerosol optical depth in the stratosphere between WACOM and the observations. You'll also note that some of the work has to be compared appropriately. This Sato et al. Data set is actually just above 100 millibars, not the tropopause. And there's a significant amount of aerosol that happens between the tropopause and 100 millibars at higher latitudes. But we've been pretty happy with the results of this. Also, the dashed lines in these labels here are individual volcanoes. So this is Mount Pinatubo, and then you can see some of all those spikes are associated with different volcanic events. What this has led to is a much better assessment of the climate impact of recent volcanoes. So this is a series of different temperature levels, and the observations are in black. These are temperature perturbations. 100 millibars, 70, 50, and 30 millibars going up in the stratosphere. CESM4 that was run for CMIP5 produced a fairly large perturbation in the lower stratosphere at 70 and 50 millibars that was much more significant than observed. And when we do this in a new version of WACOM, in a free-running WACOM ensemble, we actually get a much better fit. We don't see these really large initial perturbations and spikes in the temperature in the lower stratosphere. So that's a significant improvement that leads us to believe that, combined with the observations, comparisons of the actual aerosol burden, lead us to believe we're actually getting the right answer now for the right reasons in the model. So all this is the stratosphere, and this is essentially simulating the aerosol chemistry without any clouds, because there aren't any clouds in most of the stratosphere, at least not that interact with this. There are some clouds in polar regions that are involved with the sulfur, which is a little more important for ozone depletion, and there's been some work on that too, but I'm not going to talk about the polar regions in the stratosphere today. Do you want to talk a little about how we simulate aerosol cloud interactions and some of the problems we've been having, and how we're actually taking steps to address it, and how we'd like to take steps to address it. So the way we sort of simulate clouds in a model, and aerosol cloud interactions, is we have an aerosol, an activated CCN number, that goes into an activation code and affects the cloud droplets. We prognose the cloud droplets and the liquid water in a cloud. And then there are two key processes here, autoconversion and accretion. These are pieces of the representation of the stochastic collection process, which can't really be done formally unless you have Microphysics, which represents all the different size classes and resolves the size distribution in a bin type model. So we approximate it in bulk schemes, and we approximate it with an autoconversion and an accretion parameterization. Accretion is basically the collection of water in the cloud by falling precipitation. It's a function of the mass of rain and the mass of condensate. The autoconversion is the process of creating precipitation itself. And it's a partial representation of a more continuous process. It's a function of the cloud water, and it's basically an inverse function of the number concentration to some power. And what that means, and this is an approximation, how it's typically parameterized, if you have higher drop number, you have smaller drops, they tend to fall less, you tend to get less autoconversion. Accretion is not so dependent on number, that ends up giving you rain. So we now prognose all these things, and what we see is, as we add aerosols to the model, we end up changing the relationship between autoconversion and accretion, because autoconversion is strongly dependent on this number concentration. So going back to a volcano, so this is what I showed before. These are the satellite images. This is an intercomparison that doing with Jim Haywood and co-authors at the Met Office. These are the same satellite comparisons I showed you for the Bardabunga eruption. So this is 2014 anomalies off of a climatology where the satellite shows changes in effective radius. It does not show much change in liquid water path. The UK model, so this is HADGEM 3, the UKCA version, so it has an aerosol model and has chemistry, but it still has a semi-empirical aerosol cloud interaction. So they calculate the sulfate aerosols, and then that aerosol number is used to affect the radiation code without really feeding back on the microphysics. So they do a nice job of reproducing this without much change in the liquid water path. In our model, we have it fully interactive with the number concentration affects the autoconversion. So as you increase drop number and decrease size, the autoconversion drops, and you actually get quite a bit more liquid water path. The problem, of course, is that's really hard to observe, and none of the observations I've shown you has actually shown a significant signal in liquid water path. And that's one of the issues that we're having right now in the climate model. So we can simulate the effects of Kilauea as well. These are some global simulations. They're specified dynamics. This is actually some older simulations I did a few years ago with KAMP 5, not KAMP 6. And this again shows you the model simulates this stripe across the Pacific in aerosol optical thickness. And if you let these aerosol cloud interactions run, there's also a stripe across the Pacific in anomalies of, in this case, this is watts per meter squared of, at the top of the atmosphere in the short wave. Oh no, that's the total. It's short wave plus long wave. So it's a net cooling effect, which is actually pretty large. This is done as a difference of two simulations. The only thing different between the simulations is the emissions from the volcano, and I've fixed the meteorology. So I've reduced meteorological noise so you get a nice clean signal. So I'm not showing the full field of the radiative effect of clouds. I'm just showing the effect of the volcanic emissions itself. So these are detectable, at least in the model, effects on top of the atmosphere and radiation. And this is actually during a fairly active eruption. This is 7 kilotons per day. The level now is actually more like 3 kilotons per day. You can also detect that as well. So the question is, does this match observations? Well, the nice part is we can actually sample particular days in this model because we have specified dynamics. So this actually does correspond to individual events. I'll skip that. So for example, this is going back to, well, this is going back to what I showed you from the earlier ACE flight where you have something like SO2 and CCN, and you can see the correlation here. You can build up pieces of this with the different pieces of the data. We've shown we can simulate this in the model. So if you look at the relationship of CCN to sulfate, there's actually a quite good correlation. This is basically the nucleation process. You then start looking at some of these other terms, and it's not clear exactly what's going on, even in the model. So this is a controlled experiment, and even in these controlled experiments, here, does the drop size change with CCN? And as the CCN go up, yes, there's a little bit of an indication that at least the larger drops, you don't see larger drops at those higher concentrations. But it's not intuitively obvious there's a relationship here. Part of it is there are many cloud regimes happening. And here again, this is cloud optical depth and cloud effective radius. It's not clear there's a little bit of a relationship here, but I haven't even drawn a line in there because I don't think it's that significant. So this is gridded observations. We can also actually do things like sample the model on flight track. So I picked a particular day from the simulation, and I apologize for not quite getting the balance here, but the contours, here's Hawaii in red. The contours are in color are the aerosol optical thickness, so you can see that there is a volcanic plume coming out this way and a little bit of it coming up there. And then these are cloud decks, and these regions here are 100% cloud fraction. And these regions have partial cloud fraction in the model. Here you're getting up to 80%. And you can actually then sample the model along just some particular flight track. Just kind of put a flight track in the model and see what happens. And when you do that, you get curtains. So we get a curtain of sulfate, a curtain of cloud drop, cloud water, and a curtain of number concentration. And you can start building some of these relationships again. So we can actually see some of these relationships in the model. Again, some of them are harder to see. This is the drop number and the cloud effect and the cloud optical depth. It's pretty easy to see the first part of these correlations where we're actually activating. And if we add aerosols, we tend to get smaller drop numbers. What that actually does to the clouds is actually more complicated. So this is all kind of preparation because we don't really have a lot of these detailed observations, but we'd like to go get them. So we have a field project that's been proposed to NSF. It's called the Kilauea Aerosol Microphysics Project, KAMP. And the concept is, as I've been describing, to basically study the effects of volcanic aerosols on tropospheric clouds as a natural laboratory for what happens to anthropogenic emissions in global climate, and also to predict the local evolution of sulfur dioxide into sulfate to evaluate the air quality modeling that's done regionally in Hawaii. Science questions for this project are looking at the conversion rates between sulfur dioxide to sulfate and then on to cloud condensation nuclei. We're looking at the basic plume evolution. We need to measure the aerosols. We also want to understand how sulfate affects cloud microphysics and then cloud radiative effects. So we need to measure clouds. So this has a payload where we're measuring a bunch of properties of the aerosol and measuring a bunch of properties of the clouds. This has the advantage that we're dealing with pure liquid clouds, mostly in the marine boundary layer. So that we don't have to deal with the complexities that arise, say, from the ice phase. And then, this is actually built into the project, is the science question of can we simulate this with a particular set of models? In this case, a simplified transport model that does a simple representation of air quality, and a mesoscale model, WRF and WRF Chem, as well as a global model, CESM, that tries to do these aerosol cloud interactions. So our preliminary OSCE studies, our observation simulation experiments, they do show significant impacts of these plumes on clouds in the region. And also we have ability to separate some of these island wake effects within the models. And I think I'm probably going to stop there. I'll just show this one again, skip a couple of things. What we intend to do is to try to fly legs both across the plume, above clouds and below clouds, both with active sensors, so having a radar and a LiDAR looking down to figure out where the plume is, then coming back through the plume, measuring detailed microphysical properties in situ, and also going beneath the clouds in the aerosol layer, understand what's going into it. So it's a fairly comprehensive sampling strategy. We also need to do things like sort out what's happening upwind, and also flying in the lee of other islands that may have significant wake effects perturbing the flow, but no sulfur emissions because they don't have an active erupting volcano. So summary is that volcanoes affect climate. It's mostly a cooling effect. In the stratosphere, volcanoes end up scattering light that cools the planet just from the sulfate. In the troposphere, the sulfate itself as a direct effect is not as important as the sulfate's impact on clouds. And the lifetimes of these things are very different. We worry about continuously erupting, or we talk about continuously erupting volcanoes here because the lifetime of aerosols in the stratosphere is on the order of years. In the troposphere, it's on the order of a week. So you have to have continuously emitting volcanoes for this to actually impact clouds. We can simulate these effects on clouds and climate. Goals for this are to predict the future impact when volcanoes go off, both stratospheric impact as well as understanding potential tropospheric impacts. Another fairly large eruption in Iceland would have significant effects throughout Western Europe, for example, and also to help us understand and interpret past climate records. Particularly, volcanoes are a natural laboratory. They're a natural laboratory for their effects on clouds, and they're a natural laboratory for understanding the response of the Earth system to forcing, for the stratospheric volcanoes and for the tropospheric volcanoes. In some cases, this is a test of geoengineering and some of the approaches that people have thought about for geoengineering, both, again, in the troposphere and stratosphere. So I think these things are pretty important, and I think they also present a unique opportunity for really getting at some of our order zero uncertainties in the climate system, and we intend, hopefully, to make some more studies of that. And also, the details of this go down to the level of cloud microphysics. You cannot do it from space. There's been a lot of work trying to do it from space, and I don't think it works very well from space. And with that, I'll show Mike's movie again while I take questions. Brian.
So when does this experiment happen?
Well, it requires funding from the federal government and the National Science Foundation. So we just sent back replies to reviews to OFAP, the Observation Facilities Panel. The schedule was for June. That's the best time for the cloud, so it was June of 2018. We think operationally EOL is going to put that off at a minimum of a year. So we're probably have to resubmit in the fall, depending on how the science proposal goes. So we're going to aim for June of 2019 right now. Go in the back. Yep.
You want to speculate on why liquid water path doesn't respond very much?
There's a lot of speculation on that. I'm not really sure. We've been playing with it. Some concepts are there are essentially buffering effects probably related to entrainment and turbulence in the clouds that prevent that from happening. This has been a conundrum for a while, and there are places where you can see this. There are places where you don't see it. And you'll see small-scale modeling studies depending on basically usually proving somebody's preconceived hypothesis that their study does or doesn't contain this liquid water path effect depending on regime and depending on the model. So we're still playing with it, and we're actually pursuing the idea that there's some turbulence issues that we don't understand that are feedbacks in this process. And we're trying to work on that subgrid variability. It's hard in a climate model to get that, so we're looking at a variety of different scales. Christine, in the back.
I was just curious.
Pass you the microphone.
Oh, yeah.
Just how certain are we on the emissions of SO2 from these volcanic sources?
I'm going to let Mike or Anya comment on that one.
I'm going to let Anya comment.
I think, so for example, Kilauea we're pretty certain because, and even Bartabunga, because there were detailed measurements at the ground level that we build up those measurements. So the effusive volcanoes, the ones that stick around, I think we have a pretty good handle on because we actually can physically measure them over periods of time. The stratospheric ones.
Yeah, for the continuously degassing ones, actually we only have measurements from about 50 volcanoes, and you might have noticed in one of the plots they are mainly in the northern hemisphere. So I think the uncertainty is a factor of 2 on these ones, and it's probably higher than, the emissions are higher than we implement in the model.
And then in the model, do you assume they're constant?
We do assume they're constant.
Yeah, the continuously degassing ones are constant, which is obviously not a valid assumption, I think, if you're running over more than a century. But
Right.
For the recent eruptions in the satellite era, we have very good correspondence between the model and sometimes we have SO2 observations, but we also have aerosol extinction that we can compare to the model.
That's what this is.
Yeah. But so Anya compiled the SO2 emissions in that period, and then Ryan Neely compiled back to 1850, which is more iffy. It relies on ice core observations.
So yeah, there are, I think that's the basic message, factors of 2 uncertainty in this.
Hi, can you explain a little more how, so the big Iceland explosion back in the 1780s, 1783, why that acid fog would have led to warmer temperatures?
Well, okay, so what it does is when there's a lot of sun, I should have brought my pictures from Beijing. What it does is, this is actually, a lot of this is ash, but when you get an acid fog, when you get a fog that's really hazy, you get, in the summer when it gets warm, those aerosols actually swell up hygroscopically. And that becomes really absorptive. You can't cool in the long wave, so you don't get a diurnal cycle of temperature, which means you also don't clear out the aerosols because there's no convection, and you stabilize profile. But it means that at night you're not cooling. Your daytime highs get a little lower, but what you really build up is this nighttime heat because the aerosols are absorbing in the lower troposphere, and so they're stabilizing the profile and taking up all the water, and there's no long wave emission at night. I've seen this in Beijing in the summer with, again, it's all anthropogenic emissions, but you get this haze, really high optical depths on the order of like 2 to 4. You can't see more than a kilometer or 2. You don't really feel it in your lungs because these are hygroscopic. They're big particles that get trapped in your nose, but the diurnal temperature range is like 2 degrees centigrade. You wake up in the morning at 6 a.m. and it's 90 degrees. And you cannot see the stars. So I think that's kind of what the situation would happen is it's kind of like a summer of northern China happening in Western Europe in the 18th century.
So you showed this plot, I think, from Gavin Schmidt talking about the radiative effects of the volcanoes in the 2000s maybe being partly responsible for the slowdown in warming. My understanding from what you said is that's mostly a stratospheric effect. I guess the question is how much of that is the stratospheric effect and how much of that is radiative effects from the tropospheric processes you were talking about?
I think this is mostly stratospheric. I don't know if Anya or Mike want to comment on that, but it's mostly, I'll show the picture of it. Where was it? The simulation one. Oh. It's these sorts of things. And these actually were explosive enough to get into the stratosphere. Is that right, Mike?
Yes. And the dots that are not colored don't have SO2, so those are not included in our simulation. The gray ones.
The gray ones?
Yeah.
So it's these colored ones that are larger, and those are mostly into the stratosphere. Probably not for the explosive ones because they tend to be short. There's a few of them, like the ones in Iceland tend to be, the more effusive ones tend to last longer, and so they can emit a lot of SO2. The ones that just explode once are not emitting quite the same magnitude of SO2. And when there's a lot of ash, there's a lot of scavenging that happens. When it's gas phase, there's a lot less scavenging. So it does get into the atmosphere more.
But these include eruptions into the troposphere as well as the stratosphere
Right.
in the database.
We could actually go look at what the tropospheric effect of these things is. I don't know if we've actually done that in any of the models, but that's an interesting question.
Can you explain a bit more on how you're going to use an aircraft to look at the conversion rate from SO2 to H2SO4 if it's something that's continually degassing?
I guess one way to do it is there's a variety of different ways of calculating budgets of the conversion rates, but part of it is there's a continuous array here that indicates what the column SO2 is that's fixed, that the USGS maintains. And if you fly sections across this and look at both the sulfate aerosol in situ and with a LiDAR, as well as measuring the SO2 over time, also using passive tracers, so to understand how the emissions are diluted, so you can figure out the dilution and the scavenging, you can construct a bulk budget for how the sulfur has to evolve. And so there's not a lot of other reliable tracers. We actually think we're going to use a delta CO2. So the CO2 concentrations here can get up to 800 ppm near the vent. And then that's pretty much a dilution tracer. It's variable, but if we can measure it continuously, then that gives us a good way of figuring out what the air is doing. So it's basically a budget operation with a little bit of complexity having to do with the scavenging and the oxidation rates. There's an aqueous oxidation rate in cloud and a gas phase oxidation rate. And by looking at those things, we're hoping to actually be able to close the budget. And part of it is just to understand, can you close the budget with a simple rate? Can we actually take a simple 2 numbers for aqueous and gas phase oxidation, measure the sulfate here and the SO2, and measure it here and actually get anything that makes sense with a trajectory model? So that's kind of what we want to do to evaluate the models that exist for the air quality.
I do agree with you that Hawaii is probably the best place to go to do these kinds of experiments, but there's one problem, and that's that wake effect, or it's a disadvantage, I would say, not a problem.
Yep.
So you said you are separating that out using the models. Could you explain that a bit more? Are you removing the islands in the model?
There's two ways to do it from the model. You can remove the island, and you can remove the sulfur. And so we can do both those things. So one of the things we're doing is Allison Nugent, who's now at the University of Hawaii, who was here, has had experience in playing with those things with island wake effects. And so she's going to run some fairly detailed 200, 300 meter wharf simulations to try to sort out, take out the island, put back in the island, and figure out. The other issue is you can fly, there's a southern wake and a northern wake, and they tend to be impacted differently by the SO2. So you can measure the northern wake and the southern wake, and usually the southern wake has a lot more SO2, particularly in the season we're going to be there because you have steady trade wind flow. You can also measure in the lee of Maui to understand what the perturbations of clouds by the island look like without any SO2. So we got about a couple different ways of trying to close that problem.
Any more questions? Let's thank Andrew again.